Hello, students. In this lecture, we start talking about cryptography itself. And first thing we're going to talk about is Cipher and Julius Caesar. It's a famous Roman emperor, right? So lived from 100 BC until 44. And he was famous for, at least people say he was famous for using cryptography and sending his messages to his generals. And what is his system? His crypto system. And again, crypto system was discussed in the last small lecture. His system is really easy. It just does the following. Each character in the message was replaced by the character which is 3 positions ahead in the alphabet. So 3 positions ahead in the alphabet. And that was his idea. And it's called Caesar cipher. And a lot of times it's called ciphers for the specific system. So basically, if you have the alphabet A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, and Z. So every letter is replaced by the letter which is 3 units ahead in the alphabet. All right, so let's do an example. In crypto systems, there is always two things that we should be able to do. One is encryption. From the original message, you create encrypted one. And the other thing is decryption. So from the encrypted method, we would like to recreate the original one. And so in this example, we're going to encrypt. Or sometimes people say encode this message. So we have a message, attack the enemy. So we have this message, attack the enemy. And to encrypt this message, we have to take each letter and move it 3 letters ahead into the alphabet. So basically what happens to the letter A, the first one, you count 1, 2, 3, so it becomes D. So A will go into D. But if A goes into D, then B goes into E, right? And C goes into F, D goes into G, then we have H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. But what happens to Z? There is nowhere to go for Z. So Z will wrap around and will go in, oh sorry, I said Z, I will start with X. X will go 1, 2, and then wraps around and goes into A. Y goes 1, 2, 3, so B, and Z goes into C. So now it's really easy for us to take T and say that it's going to be W, W, D. For C we have F. For K we have N. For T we have W, for H we have K, and for E we have H, for E we have H, for N we have Q, for E we have H, for M we have P, and for Y we have B. And this is our encrypted message. So basically we take and we move each letter 3 units up in the alphabet, 3 units up in the alphabet. That's a relatively easy idea. How do we decode the message? So in the next example, we would like to decode the message. So decoding is an opposite procedure. Decode, or some people say decrypt, right? Decode or decrypt. And the message is OHD UQ WK LV OH VV R and Q. So this is the message we have to decrypt. So one way is to go to O and move it 3 units back, right? So we just do the opposite. Before we moved forward, now we move backwards. So O would move to L. Another way to do it is to go to the bottom of this 2-line code and move up, right? So from O we move to L. Then from H we move to E. If you don't like this method, you can go to E and move it, and take to H and move it 3 units back to get to E. Then for D, we go to A. Either way is going to be A. Then letter U, you find U, you move up, so you get R. You find Q, you move up, you get N. You take W, you move up, you get T. You take K, you move up, you get H. You take L, you move up, you get I, L to I. Then for V, this is V, we go to S. O, we already know it's going to be L. H, we already know it's going to be E. V, we already know it's going to be S. And R, we don't know, so we have to figure it out. R is O. R is O, and Q goes to, here's Q goes to N. So what was the message? We can figure it out. Learn this lesson, right? Learn this lesson. So pretty nice code. Easy to encode, easy to decode, but what else is easy? It's easy to break, right? This cipher. This cipher is too easy to break. Too easy to break. Why? Because you can just use brute force. What is brute force? You remember it probably. Brute force means there is only 25 ways to so suppose we don't move by 3, right? But we move by different numbers. So there are only 25 different transpositions that you can use, because even though there are 26 letters, but one is correct one, and so you need to make 25 different transpositions. You only need, in quote, right? You only need 25 different transpositions. It's tedious, it's a lot of time, but it's doable, right? So let's think about this word. Decode E, Q, Z, and P. Okay. So I would like to I said decode, right? Or decrypt, right? Decrypt this word. So you don't know what's going on, but you can You can use all possible shifts for E, for Q, for Z, so it's a fixed number, right? So you move E by 1. So let's try to do that. So E, Q, Z, and P. So we go to our alphabet. So I'll grab it from here. So if I go to the alphabet, okay, so this is our alphabet. So let's start with E. We can move E1 back, right? So our first decryption will be D for E, for Q it's P, then for Z it's Y. We're moving one letter backwards, right? So first one is shift. Let's finish it off first and then write it O for P. So shift one letter to the left. And then we do two letters to the left. So two letters to the left would be C for E because we move two letters, D and C. For Q, it's going to be O. Then for Z, it's going to be X. And for P, it's going to be N. So this is shift two letters to the left. So first word does not make sense, second word does not make sense, but if we do it 25 times, one of this will make sense. And actually I grabbed this picture from the book. Let's see what this does. So you see they did it for us. So we shift by 1, shift by 2, and then you do 25 different shifts. Why 25? The 26 one is the word itself, the 26. So it doesn't move anywhere, it just doesn't come back to the same word. But you can clearly see that 12 transposition gives us the word send. And so we broke the code. It will take a while, right? Maybe 20 minutes, maybe, or 15 minutes, but we would break it. Conclusion: we need to make our code a little bit more sophisticated, and for this we need to learn a little bit more of math ideas, and we need to review some algebra. So this is a review of algebra. Some things we actually already know. So let's go back to the idea of the remainder. And so if we divide some number, divide A by number n, A divided by n can be written as quotient plus the remainder divided by n. So A is a number, n is divisor, Q is quotient, and R is the remainder. And we already know, we did it before, if we multiply both sides by n, on the left side we're going to get this expression, then n times q plus r over n on the right. But according to the mathematical rules, we can distribute this n. On the left side, n and n will give us a, and on the right side we're going to get n times q plus n times r over n. And this number will divide into 1. So our final idea is that a can always be written as n times the quotient plus the remainder. And from this rule, we also know that we can always find the remainder to be a minus n times q. So either we're going to use it in both forms, this form and this form. So let's quickly do a short example. If we take number 10 and divide by 3, so we can take and divide using long division. So goes 3 times, we put 9, we subtract, we get 1. This is the remainder. This is a quotient. All right. So that means that 10 can be written as 3 times 3 plus 1, where 1 is the remainder. So another short example. If I take number 15 and divide by 4, then we can use long division. 15, 4, so goes 3 times, so we put 12. So it's going to be 3, that's our remainder, that's our quotient, and this tells us that 15 can be written as 4 times 3 plus 3. 4 times 3 plus 3. Right, so this is n times q plus r. So we're ready for a definition that will be really important for us. So this definition says the following: for any two positive numbers a and n, we define a mod n, and you read it as a modulo n, but it's in Latin, so people usually just read it a mod n, just a mod n, just read it as it says. So what is it is it's going to be the remainder when a is divided by n. So basically a fancy name for the remainder. So let's try to calculate 5 mod 4 for the example. 5 mod 4. So what you have to do, you have to take 5 and divide by 4. It goes 1, so you subtract, you get 1. That's your remainder. So what does it mean? We can write 5 as 4 times 1 plus 1, and this one is the answer for 4 mod 1. Sorry, 5 mod 4. Didn't say it right. This is your remainder. All right. How about 7 mod 4? 7 mod 4, so you take 7, you divide by 4, it goes 1, you subtract 4, you get 3. So you can say this is 3. Why? Because you can write 7 as 4 times 1 plus 3. Now, harder question. What is 8 mod 4? So if you take 8 and divide by 4, you're going to get 2. And if you subtract 2 times 4, which is 8, you're going to get remainder of 0. So you can say this is 0. Right? So if number is evenly divisible, if 8 is evenly divisible by 4, your remainder is 0. And so you can write it as 8 equals 4 times 2 plus 0. So tiny bit harder. 2 mod 3. So 2 you want to divide by 3, but you can't because 3 is bigger than 2. So you say that 2 is its own remainder, right? 2 is its own remainder. Why? Because you can write 2 as 3 times 0 plus 2. So 2 would be its own remainder. And we learned before how to use calculator to find the remainder. So for big numbers, we will use calculator. So for big numbers, use calculator. Use calculator. So what would be 147 mod 13? Right, so you take a calculator, you divide 147 by 13. We did it before, so you get 11.307 ... something goes on. But you know, that's your quotient, as we agreed before, that's your Q. So you take 147 minus 13 times 13 times, wait, did I write it correct? 11, I didn't do it right, sorry. 13 times 13 is too much, that's how I figured out that it's a mistake I made here. So 13 times 11, right? So we do 147 minus 13 times 11. So we get 4. And that's our remainder, so we say that, didn't put it right, made a lot of mistakes here, but let me fix my mistake. So 147 divided by 13 is this number, 11,307. 11,307, ... But this number goes over here for the answer. Another example, what we want to do, another example that we want to do is 356 mod 11. So we take 356, we divide by 11. 356 divided by 11 is 32.36 ... So whole part is 32. So we take 356, we subtract 11 times 32 to get our remainder. So let's do this out. 356 minus 11 times 32. So we get 4 again. It's just coincidence. It wasn't intended this way. Okay. So again, we know how to do it. We've done it before when we did what did we do? We did money order, right? For the money order scheme. But let's talk a little bit about modular arithmetic. Modular arithmetic is relatively easy. So let's look at a few examples, and from examples we'll create some rules. We did it many times this semester. If we take 7 mod 3, what would be the answer? 7 mod 3, we know that if we divide 7 by 3, we get 2 over here. We subtract, we get 1 as a remainder, so the answer is 1. Then if we take 4 mod 3, 4 divided by 3, it's 1, and you subtract 3, you also get 1, so it's also 1. So if you take 1 and add it, you're going to get 2. Right, but also if you take 7 plus 4 and calculate it modulo 3, what would you get? Let's do that. So 7 plus 4 is 11. And 11 mod 3 is, you take 11, you divide by 3. Here we don't really need a calculator. We can do it by hand. So we write 3, we subtract 9, we get 2. So this is 2. So that means this is also 2. So I'll raise a question mark. And you see that it just works, right? It just works. So what do we say for the rule? We say that the rule is if B mod n is equal to A and D mod n is equal to C, then B plus D mod n is equal to A plus C mod n. And that's our rule. This is our rule. Let's try to see if it's also going to be true for difference. Suppose 19 mod 5 is equal to what? Let's think. 19 divided by 5. So we write 3, we put 15, we subtract, we get 4. Alright? And then if you take 16 mod 5, 16 divided by 5, we write 3. So we get 15, we subtract, we get 1. 3 times 5 is 15, so we get 1. And if we take a difference here and here, let's see what we're going to get. 19 minus 16 mod 5 is equal to 3 mod 5, but we know that if this number is smaller than this number, then the answer is just on the left, so it's going to be 3. And you can clearly see that 4 minus 1 is also 3. So what would be the rule? The rule would say if B mod n is equal to A and D mod n is equal to C, then B minus D mod n is equal to A minus C mod n. That's arithmetic works. Next example is multiplication. Multiplication is a little bit harder to comprehend, but let's try it. Multiplication. So what would be 23 mod n? 23 mod n. I said n, we need a number. So let's say 4. So we take 23, we divide by 4. I'll move it a little bit to the right. 23 divided by 4, so we put 5. We subtract 20, we get 3. So we put 3 over here. Also 6 mod 4. And 6 mod 4 is really easy because 6 minus 4 is 1, right? So 1, we put 1 times 4 is 4, 6 minus 4 is 2. When the numbers are very close to each other, you can just subtract 6 and 4 to get 2. So let's multiply on the right and on the left. We'll have 23 times 6 mod 4, which is equal to, so we're going to multiply 23 and 6, so we're going to get 138. 138 mod 4. Then we're going to take 138, we're going to divide by 4 using calculator. Mistake. So we get 34.5. 34.5. And to find the remainder, we take 138. 138 minus 4 times 34. 138 minus 4 times 34. Because 4 goes into 138 34 times. We're going to get answer 2. All right, so let's do this out. So our answer is 2. Our answer is 2. Right, this one goes here and therefore goes here. But if we multiply 3 and 2, we're going to get 6. They are not equal. What did I do wrong here? What did I do wrong? And you can think about it a little bit, but the main thing that probably is not that clear that 6 is bigger than 4. That's our modular calculations, modular. I didn't do 6 mod 4, so I need to finish it. I have to calculate. Basically, I haven't done the last step. I need to calculate 6 mod 4. And we know 6 mod 4 is easy to calculate. You just have to take 6 and divide by 4. So you get 1, you get 4 on the bottom, so you get 2. So it works, right? It works. I just have to I have to just finish my calculations, which I have not. Finally, we can put the rule for multiplication. If B mod n is equal to A and D mod n is equal to C, then b times d mod n is equal to a times c mod n, and that's our rule. But the consequences of this rule are very important. For example, if you have b to the power d mod n, you can do b mod n to the power d if d is an integer. Actually not integer, but positive integer. So basically you're going to write b times b times b times b times b d times, and you can apply this previous rule and you will get this, right, to show that this rule is true. So that's probably good enough for this lecture. In the next lecture, we're going to come back to the Caesar cipher and we'll try to use this modular arithmetic to redo it, how we do calculations for the Caesar cipher. And if I understand how to redo it, we're going to create a more complicated cipher. And I'll see you in the next lecture.